Okay, so just a reminder that your assignment 2 is due sometime soon. There was a little confusion about the date. It was written wrong in 2 places, so I just pushed it to the later date. But March 19th is when it's due, and you have everything that you need in order to do it, and we went over it another class. But is there any questions about it or anything else? Okay. Okay, so today we'll wrap up the attack tree on HTTPS. Okay, so you'll recall it's been a while now, but you'll recall that we were talking about these certificates. And certificates come in 2 flavors. There's the flavor that tries to bind Concordia University in Montreal into both the public key and the domain value. And then there's certificates that just bind the key and the domain. They don't try to go for who Concordia is as an entity. So these are called EV certificates. These are called DV certificates. EV certificates show up as green. They did. Now they basically don't distinguish anymore. But this was historically how they would distinguish them. And to get an EV certificate, it's some sort of in-person process. And the big problem with that is if you forget to renew your certificate, or if you need a certificate very, very quickly, because it's an in-person process, it takes hours or days, maybe weeks, in order to get it. And so what people want is basically an instant way, or as close to instant as possible, to get a certificate. So what CA's introduced was they said, okay, we can do an automated certificate, but we can't figure out who you are as, like, whether you're Concordia, the university, or whatever. But what we could probably do is figure out whether you control a domain, because controlling a domain is something that could be automated, as you'll see. So the idea here is that the CA will sign your certificate. You'll show up, you'll say, here's my public key, I own Concordia.ca, and the CA will say, well, you need to prove that to me, okay? But now instead of proving it to a person, I'm proving it to a computer at the CA. So the CA is just going to look at digital evidence. It's going to be cheaper and faster. I can basically get it right away because there's no human involved. The CA is not paying someone, so it's cheaper for them to issue it. It's still vulnerable to what we call name squatting. So let's say, for example, I own Google, but it has 3 O's instead of 2 O's. I can get a DV certificate for that because that is my domain. I do own Google with 3 O's, okay? Is that the real Google? No, it's not. It's not Google, the company in Mountain View, California. And so I couldn't get an EV certificate for that, but I could get a DV certificate if I actually own that domain. So it doesn't solve that particular problem, but other than that, it should correctly bind a public key to an actual domain. So there's 3 ways of doing it, and they're all very, very similar. So we'll start with what's called email-based verification, and then we'll look at 2 variants just quickly because the threat model for them are almost the same. Okay, so this is how it's going to work as a process. So I'm going to show up at the CA and say, I'm Concordia.ca. And the CA will say, I have no idea. Maybe you are, maybe you're not. Okay? So what the CA is going to do is it will generate a random number, and it will email that random number to admin at whatever domain I'm claiming to be. So if I'm claiming to be Concordia, it will send it to admin at concordia.ca. All right? If I'm actually Concordia.ca, I can go into that email account, and then I can get the code, and I can copy and paste it into a box on the website, or maybe it just embeds it in a link, so I just click on the link, and then that's done. Okay? And then what the CA will say is, well, because you were able to go in and get that email, I believe that you control that domain, therefore I'll issue the certificate. Okay? So it's pretty simple. Now, put on your security hats. Okay, pretend you don't own the domain, and you want to get that certificate. Is there any point in this procedure that looks like it might be vulnerable to you being able to get it? Okay, so what's be a little more specific? Yeah.
Maybe they hack the number that they sent to the email.
Okay, so let's say the number is not very long. Say it's a 4-digit PIN or something like that. Could I guess it? Probably. It's just a machine at the CA anyway, so maybe I can try a couple times before it locks me out, or maybe I can try lots of times. Okay, so that could be one. So the way to counter that, what's the solution to that problem? Just pick a long random code, something that you couldn't guess. Yeah? So that's fine. So we can probably fix that problem, but it's a correct problem. So that's one way of attacking it. Any other ideas? Yeah.
Even if we had that, the certificate was, even if you had this code or whatever, I think you don't really gain much though, right? Because the certificate goes to a domain, you intercept that PIN or whatever it is, but what do you gain from that? I think.
Okay, so let me back up a bit. I maybe didn't explain this well. The answer is sort of with this CSR thing. So what happens is before this process starts, I show up and I say, I have an unsigned certificate and it has my public key in it. Yeah. So I want a certificate for Concordia even though I'm not Concordia. What I'll do is I'll create what looks like a proper Concordia certificate. It will have their address and all that stuff. But when it comes time to put my public key in, I put my personal public key in. Yeah. Then I go to the CA and I say, will you sign this? And they're just saying, yes, I will sign it if you give me that code. If you can tell me that code, I will sign it.
Okay.
Does that make sense? Yeah, yeah.
The code can be forward.
Can be forward?
Forward.
Like.
Forward to other who is not the real owner.
Okay. So it's going by email to this email address. Yeah. So there's a couple attacks there, but if you have one in specifically. Okay, how do I get the link? I need to.
If I have access to the email.
Okay, if I have access to the email, how do I get access to the email? What protects the email? Why can I just a brute force of what?
ID and password.
Okay. So this email probably has a password with it. Okay, so if I guess the password, I'm in. Okay, so that's one way I can do it. This email is probably sitting on a computer physically somewhere. It'll be sitting on a server. If I get physical access to that server, probably I can get access to it. Yeah? What if I own admin at domain.ca? What if I go to Concordia and say, I don't want j.clark at concordia.ca, just give me a min. That's a cool name, right? Then what happens? Then I'm able to get the certificate for it, okay? Now that sounds dumb, but there's things like Gmail. Can you register any domain or any username? You have to be the first one. So what Gmail would have to do is they would have to know that CAs are issuing certificates using a min, and they would have to reserve that for themselves. They'd have to say, you're not allowed to register admin. Yeah? Now, how does Google know that? How does anyone know that admin is a special email?
They don't, but it's assumed.
Okay, so it's assumed. Now, here's maybe a dumb question. What does admin mean? Why is it admin?
Because he provides access to everyone.
Okay, but the thing I was looking for was simpler, which is it stands for administrator. Yeah? Okay. What language is administrator in? It's in English. Does everyone in the world speak English? Okay, so if you were in a different country, could that be the word for administrator in a different language? Or the short form for administrator in the other language shortened? Probably, right? That's reasonable. So now Google has to know about, oh, how do you say administrator in every other language, right? I got to save those emails as well, right? And so it's really up to just the CA to, it just takes one CA to have a weird thing that they allow you to send the email to that nobody knows about, and then all of a sudden you can go and register that, okay? So that actually happened in real life. So one CA in the world would send these passwords. You could have like a drop-down menu, so you could choose admin or hostmaster. There's a couple different ones. And one of them was SSL certificates. So they would send the challenge to sslcertificates@domain.com. And Microsoft and Google, they didn't know about that. They didn't know that there was a CA using that term. So they didn't save that or reserve that email. So someone went to Microsoft to live mail, and they just registered SSL certificates at live.com. Microsoft said, fine, here you go. And then they went to the CA and said, give me a certificate for Microsoft, like for all of Microsoft. Like live.com would be like, you know, like you could sign code, like going to Windows, like drivers, like, you know, and they got a certificate for it. Now this was a white hat hacker, and so they disclosed it. They didn't use it for anything, but they just proved that it could be done. What about the email going across the wire? It has to go from the CA to the server. Is that encrypted? Okay, do you use PGP? Does anyone use PGP? Okay, so there are things like PGP. That's right. It does give you encryption, but most people don't use it. Let's assume that you're not using PGP, like most people. Is there encryption in that case? This isn't some special case, so let me just ask in a more general way. You email anybody, is that encrypted? Or could someone in the middle that happens to be, you know, the Wi-Fi router or whatever, mail servers in the middle, could they just read what that email says?
Depending on the protocol. So use STMPI. I don't remember.
Yeah, SMTP is probably the name you're looking for. So there's a protocol between you and the mailbox.
Yeah.
So it's either IMAP or SMTP, or POP. Sorry, yeah, POP3 or IMAP. That does provide encryption. Or if I log into Gmail, I'm accessing Gmail over HTTPS. So I do have encryption from me to my mailbox. And then SMTP is the one that would send it from the mail server of the CA to the mail server of your domain, whatever domain you're trying to get a certificate for. Okay, encrypted or not? Probably should be. Yeah, so the answer is it's not. Okay, so a lot of people don't realize it, but email is not encrypted. Okay, now that's not to say it's exactly just going across the wire in plain text. What they do is they cheat a bit. So what they'll do is they'll just say, hey, tell me your key, and then the server will tell you the key, and then they will encrypt it under that key, but they'll believe any key that they're told. So the adversary has to get in the middle when they're asking for a key, then the adversary can drop their own key in, and then from there on they can intercept any traffic that goes across it. So we call that opportunistic encryption, or we call it trust on first use, where you try to connect, and if you get the correct key the first time, you're protected, and if you don't, you're not protected. Okay, any other weaknesses in this protocol? Okay, so I think we got most of them anyways. Let's think about it. Okay, so we get access to the mail server, we get access to the code, then we get a certificate. If we can guess the password and log into that account, then we can get the code and then get the certificate. If we intercept the email, and it's using the standard email approach, SMTP, then it is not encrypted in the same way that HTTPS is encrypted. It uses this trust on first use, link-to-link encryption. If you can just guess the challenge value that's going across, that would be another way. If it's some sort of webmail or some domain where people are handing out emails, like you can request certain emails, even in an organization, you could be like, okay, this is the email I want. Then you could register at one of these special email addresses. Okay. Now I mentioned admin, hostmaster. I mentioned SSL certificates was a weird one. How many of these like special domain or names would you guess that you have to set aside? Like, would it be like 5 or 5 million or 5,000?
Could be thousands if you include like foreign names or other languages or whatever.
Okay, yeah. So it's a lot higher than you would think. So initially I thought it would be like not a lot. So this is just about the person who was able to register SSL certificates at live.com. Then they were able to get a certificate for live.com. And then here's a list of some of the addresses that you're supposed to reserve. So not all of them are used for SSL, like abuse at domain.com would be for like reporting purposes. But these are things that you're not supposed to hand out to your users. And the number of them was here somewhere. Anyways, this person came up with maybe 20 of these that were important. And then people said, oh, no, you missed a whole bunch. And so then this person said, oh, we have like a GitHub file that has all the emails you should reserve, and it's 1,250. So it's a lot. So you have to know that as a domain. As someone who manages a domain and manages an email system. Okay, here's another one I didn't mention. Let's say that the CA is going to send an email to admin@concordia.ca. How does that email actually get to admin@concordia.ca? Well, the CA has to go over to DNS, get the IP address for concordia.ca, and then it's going to send it to that IP address, and it's going to say this is for the account admin, and then the mail server will accept it. Okay. Now, how do you get the IP address for a domain? We talked about this before. DNS. Okay. So DNS has different records, and so what you could do if you wanted to is you could say all the web traffic coming to concordia.ca go to IP address A, and all the mail go to a different IP address. So you could have different machines, one that's doing the web hosting, one that's doing the mail, and then there's other things that you could set up. So the place where you put the mail server IP address in your DNS record is called the MX record for mail exchange. So anyways, if you look at someone's domain, you'll see that they have an MX record, and then there'll be an IP address there that may or may not be the same as their normal IP address. And then that's where you're going to send the email. Now, what if I'm able to write my own IP address in, right? Then the email's coming to me instead. Yeah? So any kind of attack on DNS, so it could be like DNS cache poisoning, whatever. There's a bunch of different ways of attacking DNS. Those attacks would work. It could be as simple as, like, why can't I just go and change Concordia's DNS record? Well, they have some username or password that protects it, right? So if I can guess that username or password, then I'm in. Okay, so another username password that comes down. You could maybe try some social engineering. I'll tell you a story about that, like in another lecture as well. But anyways, any way of attacking DNS would also be sufficient. Okay, so this protocol is, I guess it kind of works, but it has a lot of vulnerabilities. There's a lot of surface area that you could try to attack. Now, there's two other variants for automatically issuing certificates. The first is that you just put your certificate request at like some web page on your domain. Okay, so you could put it at domain.ca/csr.text or whatever. The CA will tell you where to put it. They'll say, go put the file here, and then I'm going to go through the internet to that file and pull it off of the website. And if it's sitting there waiting for me, then I know you must control the website. Okay, so this one's very similar to email. Now, okay, so one small thing is when I go and fetch this text file, the CA will do it over HTTP. It won't do it over HTTPS. Why is that? Why do you think that's the case? If it does it over HTTP, that means if there's a man in the middle, the person can just change the key. Or say that file doesn't exist on the domain, the person in the middle just intercepts that request and then drops in the file as if it does exist on that domain, even though it doesn't. So it's vulnerable to man in the middle. We could get rid of that if we used HTTPS. So why isn't the CA? CA knows what HTTPS is. It's in the business of issuing certificates. Why would it not fetch that over HTTPS?
Because that's what we're trying to get started with.
Okay, so
We don't have the certificate yet to do it.
correct, yeah. So there's a circular dependency here. So in order to fetch it over HTTPS, the website would have to have a certificate. But why are we doing this process? Because the website's trying to get a certificate. So it doesn't have it yet. So the CA cannot assume that you already have a certificate because it's trying to give you a certificate. Yeah? So that's why it has to go over HTTP. So anyone that's in the middle could intercept that, just like the email. They could change it and put their bad public key in this file. Then it has a lot of the similar dependencies. It depends on DNS, and it depends on those are basically the same ones. So man in the middle, DNS, password attack on the domain itself. So the domain will be a server sitting somewhere. You could access the server. You might be able to upload files to a website. You have to be careful also about websites that host content for you, right? So if you run there's no good example of it. There used to be examples like GeoCities and things like that, where, they're just like domains where you could go and you could register your own website. So I could get geocities.whatever.com/pulpspy, and then I can put whatever files I want on that. So you have to be careful if you're running one of those services that people can't put files in the locations that CAs would be looking for this type of information. The last thing you could do is you could just put your public key in your DNS record. We're looking at DNS anyways. So you just say my key's in my DNS record, and then the CA goes and fetches your DNS record and then sees that it matches what you're requesting, and then it signs your certificate. So again, there's similar threats. The man in the middle here would be between DNS and the CA. We already talked about the fact that DNS is not secure, usually, right? So it doesn't go over a secure channel. You could do all your standard DNS attacks as well in this case. Okay, questions about any of these methods? Okay, so you might not remember these questions, but this was like leading us to why we're talking about the things that we're talking about. I'll just review them because it's been 2 weeks. So the first issue we said is I want to know, like, I'm connecting to Concordia for the first time, never connected to Concordia before. I have no idea what their public key is. Okay, so I go to Concordia, and Concordia is like, no problem, I have a certificate. And I look at the certificate and I see that it's signed by a CA, and I say, well, how do I know what the CA's public key is, right? Like, now I know Concordia's public key, but I need to know the CA's public key. So it seemed to, like, the certificates didn't seem to really solve the problem. So how do I figure out the certificate authority's key? And the answer is it comes bootstrapped in my computer. So before I even turned it on, it was put into the hard drive of my computer by Apple themselves. And that's how I learned some CAs. And then CAs can issue certificates to other CAs, and then they can ultimately issue it to websites. And then we said, well, why can't I do the same method? However I figured out what the CA's key was, why can't I figure out Concordia's key? So that's sort of a roundabout way of saying, why isn't Concordia's key inside of my computer, right? And you could try to do that in a world. The problem is that the websites change on a daily basis. There's hundreds of thousands of certificates that expire every day. There's new domains that are registered and things like that. So there's no way you could load everyone's key onto a laptop. So that's why we just load the CAs, because they're kind of permanent. They've been there for 15 years. They're going to be here for another 15 years. They don't change so much. And then they'll issue the certificates for the websites. Okay, then the other issue we said is I have no idea what Concordia's public key is. That's why I have all these CAs and stuff like that. How does the CA figure out what Concordia's key is? It signed it, so it somehow had to figure it out, okay? And so that's what we were just talking about. So it's either the person went with, a business-to-business transaction, or they did one of these domain loops where they got an email sent to admin at their domain or something like that. They satisfied the CA that they control the domain, and so the CA said, okay, that must be your public key because you're the person who actually owns that domain. Okay? Now the final question we could ask is, can we do what the CAs do? The CAs figured it out. Why don't we just do it? Then we don't need CAs. Okay? So let's go through the three options. So could you do like the EV verification of every website? So you probably can't do that. Like if I want to go to Concordia and Concordia's like, this is my key, I'm not going to be like, okay, send me a bunch of business documents in the mail and I'll check them all out. It's easier for the CA to do it once than for every user to do it. Okay? What about email? So technically I could go to Concordia and they could say, here's my public key, and I'll say, I don't quite believe you. I'm going to send an email to admin@concordia.ca, and you can respond to that, and then I'll believe that that's your public key. Okay? So as users, we could do that. We could have our computers configured to sort of do that kind of thing automatically, but it's a lot of email going back and forth. Again, it's probably easier for the CA to do it. Okay? The website is similar to it. And then the DNS one is the interesting one. If the website just put their public key sitting in DNS, right? They put it in DNS for the CA to look at and issue the certificate. Why can't I just get it from DNS? I mean, if the public key is just sitting in DNS, I have to go to DNS anyways, right? I already have the DNS record for the website. So why don't they just stick their public key there? I'll pull it out of DNS. And now I have their public key. I don't have to ask for a certificate. I can just immediately do HTTPS.
DNS is hard to see. Recording DNS is hard to be expired.
Yep. Okay. So that's one thing. So one thing is the key will sit there until they change it. Yeah. But they could expire it themselves. So every 2 years they go and refresh it or whatever. But you may have issues there. So like there's more to a certificate than just a key, and DNS records are pretty small. So like just sticking a key there you wouldn't have all the information that would be in a certificate. And if you tried to put all the certificate information, it's probably not enough.
But the cache of every endpoint, they still have the DNS records. And if it's not be updated, the endpoint near the a certain DNS server will be the old one.
Okay, so let's say that I need to change my key for some reason, right? Then I can go change my DNS record, but does that instantly update everyone's DNS? It doesn't, right? It sort of propagates from my registrar, it tells other people, and by the time your DNS resolver hears about it, it might be 3 days later, right? So they might keep using the old key. Now, if I use a certificate instead, is that a better situation? So we don't know yet. We actually have never talked about what happens if you lose your certificate key. Can you somehow revoke your certificate? What does that look like? So we'll get there. So that will be something later. But yeah, revocation, expiration, those are complexities with DNS. The big problem with it is just that when you get DNS, it's not signed, or there's no encryption or anything. And so all it takes is somebody, like say your Wi-Fi router, and when the DNS record comes to you with the key, they just swap out the key for their own key. Yeah. So if we could solve the secure DNS problem, if we could have DNSSEC, we probably could actually just start putting public keys in DNS records. And it would work reasonably well, and we could get rid of CAs. There's a proposal for that called DANE. There's a whole standard for it. But But anyways, I'll talk about it here. So why can't we use the same method? So sometimes it's better for the CA to do it once than instead of having every user do it. But with public keys and DNS, that's sort of a special case because we're already checking DNS anyways. And so if we had wide adoption of DNSSEC, then we could put keys in DNS records, which is called DAME. And if we had DAME, we actually wouldn't need CAs anymore. CAs could just sort of disappear. You still have CAs that are part of the DNSSEC system because DNSSEC means that DNS records are signed. And so you have to have like a certificate authority that ultimately signs over on DNSSEC. So you're kind of pushing your CAs around. You're not really eliminating CAs, but you could get rid of all the HTTPS CAs. So anyways, this is something for the future, but we're not there yet. Okay, so some lessons learned just about this middle part is certificate authorities, they're not actually authoritative over anyone's public key. They don't know any better than you or I what Concordia's public key is, okay? They just have been in the business of doing it, so they have processes and they have procedures. But at the end of the day, they just rely on DNS and email going to the right place and all of that type of stuff. They don't actually have any special knowledge about this stuff. And then the other interesting thing is when we talk about HTTPS, sometimes we sort of hold it on high because it's pure cryptography, right? It's like cryptographic keys and you're using AES and Diffie-Hellman and all these like real cryptographic protocols. And we contrast that with like websites with passwords and cookies and things like that. So you have the world of passwords where people choose weak passwords, you could guess them. And then you have the world of HTTPS where everything's like cryptographic keys and all that type of stuff. But as we just saw, if you can get passwords for admin@domain.ca, if you can get a password for the DNS registrar, there's a couple critical passwords, but if you can get them, you can get a certificate, and if you can get a certificate, then you can intercept all the encrypted traffic, even if it uses really strong keys that you'll never be able to guess, right? So this whole world of cryptography actually just kind of falls apart based on passwords and resetting passwords and all those like typical mechanisms that we normally use. So it's not actually a more like kind of elite technology. It's the same. So if we want to throw this stuff into an attack tree, we can look at what would it take to actually get a valid certificate for a domain that I don't control. I don't own Concordia. I want to get a certificate anyways. So what I could do is I could try to hack a CA, then I could get one. I could somehow get the CA, I could trick them to issuing me a certificate for them. So if it's some sort of EV certificate, it would be some sort of social engineering attack where I pretend that I am the company even though I'm not. And if it's a DV certificate, then we'll just look at the email case, but we have all the things that we literally just talked about. So like guess the password, intercept the email because it's not encrypted, attack DNS, get one of these reserved email addresses, change the MX record in the DNS for it. We can also, if we're a government, we could just go to a CA that's in our country and say, give us certificates for Google and Facebook. And they can't really do anything about it. Another thing that I didn't talk about, there's no slides about, but I'll just mention it, I threw it in the tree, is sometimes you have software that does a man-in-the-middle attack on you, but it's doing it for good purposes. So the two use cases for it would be, one is if you work at a company, the company may want to monitor what's going on, what their users are doing online, and they may want to inspect HTTPS traffic, which they can't do. That's what HTTPS protects against. So what they'll do is, because they're giving you your laptop anyways, they'll put themselves as a root certificate on your laptop, and then they're able to create certificates for any website that you try to go to, and they will man in the middle it, and then they'll forward it onto the website, and then when it comes back, they'll decrypt it, then they'll re-encrypt it for the key that you have with them and send it to your computer. So your computer, it looks normal. Like you still have the lock and everything looks normal. It's just that the traffic is being intercepted in the middle. Now, the one thing that would look a little different is if you went to a certificate and you clicked on it And somehow you knew that, hey, Google, they always get their certificates from DigiCert or whatever. And then you looked and you saw, oh, it's Concordia issuing this certificate. That's weird, right? So that would be like the one sign that you could see. But other than that, you wouldn't have any errors or anything like that. Okay. Now, what stops this from happening? Like, say I have a Concordia laptop, so is that happening to me? Well, it depends on whether they were able to install that certificate on my computer or not. So if I'm reasonably sure that they didn't put a certificate on my computer, then I don't have to worry about these interception proxies. Unless what if there was a company that somehow became a real CA and they put their certificate on these devices that do these interceptions, right? And so that's something that should not be allowed. CAs shouldn't be able to do that. But there were some security researchers, and they went to one of these big security conferences, and they were talking to some of the vendors there. And some of the vendors were like, "Oh yeah, we have these interception proxies, and they work. Like you don't have to change the client's computer at all. You plug it in, and it works." And the researchers are like, "That's impossible. Like that doesn't work. That breaks HTTPS." So they bought one of them, and then they analyzed it. And what they realized is that they actually had a real CA certificate in them. So when you buy the device, it comes with a real CA certificate, and then your computer already trusted it. I don't have to put my weird root certificate on your computer. You already trust this certificate that's on this device, yeah. And then so anyways, then it was published, and then all those CAs got revoked. Everyone freaked out and said, because anyone could lift that certificate off of that machine, and they could create certificates for any website on the internet. The other place it shows up is sometimes it's within your own computer. So if you have antivirus software, sometimes it will inspect your HTTPS traffic. Again, it's looking for malware or whatever, but it will do the same trick. It will put a root certificate on your computer, and then it will intercept all of your traffic, decrypt it, and then re-encrypt it as it goes out. And then parental control software, that type of stuff, also will do the same kind of thing. Okay. Now these things are a little bit dangerous because it's like a tunnel. So you see the tunnel between you and the software that's intercepting you, but you have no idea what's happening on the other end. You don't know if they're using a tunnel, if the tunnel they're using is secure. You don't control it. It's not end-to-end encrypted. And so there were some people at Concordia that did a study. They got, I don't know, maybe 50 of these different things, and they went through them, and they realized that the way they implemented SSL was not up to standards at all. There were a lot of vulnerabilities that were left in this stuff. Okay, now there's a few other things that I want to talk about. So this is sort of one aspect of the tree, but we're going to explore a bit more. Okay, so before I lead into it, I just want to talk a bit about what does it mean after you get the certificate. So we're now at the stage that we know how you get the certificate, we know what the CA is looking for, all of that type of stuff. So that's good. So what will happen is I'll go to a website and I'll say, I want to talk HTTPS to you, and the website will say, great, here's my certificate. Okay, so now I'm holding the certificate in my hand. I got to figure out whether it's valid or not. Okay, so what am I looking for in the certificate? Like what determines whether it's valid or not? So for example, who has to sign this certificate? So I'm holding a certificate. Is it okay that, that Jeremy Clark signed the certificate? Okay, it has to be a CA. And what does that mean a little more concretely? What is a CA? I'm Jeremy Clark, I'm a CA. Is that good enough?
Actually, Jeremy Clark use standard protocols and...
Say I speak all the standard protocols and things like that, but am I actually a CA?
No.
And why? I'm not, you're right, I'm not. So I'm not on your computer in your root store, or I wasn't given a certificate by someone who was. Yeah? So that's the definition of a CA. Okay? So I get a certificate, I want to know, is it actually signed by a CA, and is that CA, does it chain back to something that's in my computer? Yes or no? Yeah? So, okay, so that's one check. So that's good. Any other checks? So we talked about expirations. Okay, so certificates are valid for a certain period of time. So I got to make sure that I'm still in that expiration window. Sometimes weird things happen. Like sometimes, let's say your computer really runs out of battery. Like say you leave it for a month or something and you don't turn it on. And then when you turn it back on, the clock gets reset. Okay, so your computer thinks it's 1980 or whatever, and you don't realize it. And so you start going to websites. What do you see? You see error, 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 right? And so because your clock is set wrong, it thinks that all these things are expired or they don't exist yet, or I don't know what it thinks. But anyways, it gets confused. So that's one thing. If a lot of people get certificate errors, they're like, check your clock. That's like the number one advice. So expiration, that's fine. What else? Anything else? So there's some really basic things that are almost too basic to say, but let me give you an example. Let's say I go to concordia.ca and they say, great, here's my certificate, I'm facebook.com. Am I going to accept that certificate? No. Okay, so the domain that I'm visiting needs to match the domain in the certificate. Yeah? Okay, let's see how we did. So is it signed by a CA that actually traces back to a root CA? Is the name, the domain name, which is called subject name, that's the official name, is the subject name of the certificate the same as the website that I'm going to? So the website that's giving me the certificate, do they match? Here's another one. So CA, what's the difference between a website certificate and a CA certificate? The difference is that there's just a flag that's in the CA certificate that says, yes, this is a CA. CA equals true. And then if I'm a CA and I issue you websites, I will set that flag to false. So what that means is you get a certificate, but you couldn't pretend to be a CA and start issuing certificates yourself. I mean, you can do it, but they'll be rejected because clients will check whether you're actually a CA or not, and they'll see that that flag is set to false. So this is what it looks like. So here's Concordia. This is their website or their certificate. And you can see that there's a flag called Certificate Authority, and it's set to no. And then if I move up from Concordia to the intermediate CA, so the certificate here, both of them are certificates. They look almost the same, right? They both have public keys and addresses and names and all that type of stuff. So the difference between this certificate and this certificate is there's no difference in terms of the certificate itself, right? But what makes this a CA certificate is that this flag was set to true, okay? And it was set to true before the root signed it. So the root certificate signed it with the fact that it was true. If you go to a CA and you say, will you sign my certificate, and you sneakily set that flag equal to true, and the CA doesn't notice it and signs it for you, then congratulations, you're now a CA. Okay, so that's all it takes to be a CA, is just to have someone that's already a CA or a root CA sign a certificate that has that flag set to be true. Then you can be a CA. Then there's expiration, and we'll talk about this revocation idea. Okay, so the reason I'm going to split, or the reason we're going to go through all 5 of these is because there's some stories about these things going wrong. So I'll tell you kind of like one story about each of these. Okay, so the first story, this happened in 2014, so a while ago. It's a software vulnerability. It's called Go-To-Fail. And this affected Apple computers, okay? And it was in Apple client computers, and Apple's version of SSL, or their like software stack, is called S-Tunnel. Sorry, it's called Secure Transport. And this is the version where it was, okay? Now, there's nothing wrong with the SSL, the protocol. This is just purely software. So I want to like kind of walk you through what happened at the software level because it's interesting, but we'll just do it at like a very high pseudocode level. Okay, so the template of the code looks kind of like this. It basically says we're going to have a variable, we're going to call it check, and check can take one of 2 values, either a 0 or a 1. And if it's a 0, that means we're happy. And if it's a 1, that means we're not unhappy. That means we're not happy. We saw a check that did not pass. One of the checks failed. We'll set check equal to 1. Okay? And so at the end of this process, I'm going to return whatever's in check. If I return a 0, then that means you passed all the tests. And if I return a 1, that means that that you didn't pass at least one of the tests. Okay? All right, so what I'll do is there'll be some condition, and I'll check it, and I'll write the variable into whether it passed or not into the check variable, and that's it. Okay, and then I'll check condition 2, and I'll write it in. I'll check condition 3, check condition 4. Okay, now the only thing that's like slightly fancy about this code is, let's say that I fail on condition 2. Should I check condition 3 and 4? There's no point, right? I'm failing anyways, right? So I might as well just give up. Like, why waste the computation? Okay. So what they did is they said, if this check equals 1, then go to fail. So go to fail means that you skip all this code and you go down to the thing that's flagged fail, and then you just return check right away. Okay. So the code will basically check condition 1. If it's a 0, which is good, then it will go to the next line. But if it's a 1, which is bad, then it will just jump directly to returning a 1 to whoever called it. Okay? Is there a problem with this code?
You shouldn't use go to. It's not.
Okay, so that's one thing first. So go to people don't like. Okay, setting that aside, is there a problem?
Is there still more fail? I mean, condition 3 or condition 4 they all fail. Say you don't know about that. You will not do.
True, true. So that's another thing that could be a little better. So when I get the return back, I just know something failed. I don't know which exact thing failed. Yeah. So that it could be more verbose, for sure. Any other, like, actual security issues? Okay, so it's a trick question. There's actually no problem with this code. Okay, it's fine. This code is fine. It's not great because of the use of goto and things like that, but there's no actual problem with it. The problem is this isn't actually the code. Okay, the code that was in secure transport looked almost like this, but there was one small difference, which is somewhere in the middle, someone accidentally put goto fail twice. Maybe they were copy and pasting something from somewhere else. Maybe it was like a very subtle thing that was inserted by, the spy agencies in the US. No one knows. Okay, we can't say why it's there. But anyways, there was just a second goto fail somewhere in the middle of this type of thing. All right, is that a big deal? Yeah, why? Help me understand why that's a big deal.
Essentially, the second addition of go to fail should always run. When the check of condition 2 is done. Well, obviously, if it's true, it will go to correctly to fail and return 1. But if it's not, it should go to fail again and never essentially check condition 3 and 4, right? I think.
Okay, so let's walk through this. So let's say that we pass condition 1, okay? Check is not equal to 1, so we don't go to fail. Then we check condition 2. If it fails, then check is 1, we go to fail, we return that it failed, that's fine. Let's say that we pass, okay? So we pass, is check equal to 1? No, okay. So are we going to run go to fail? Okay, so what's the next line of code we'll execute? Okay, but they're both indented, aren't they both under the if? Is it if this, then this, both of these lines, or just the first line? Why just the first? They're both indented. Okay, so it depends on the programming language, but indents don't mean anything. If there's no brackets, normally you would do an if statement, you would put a bracket, and everything in this block is part of that conditional, okay? If you don't have an if, then it's considered just the next line, okay? The next line ends at this semicolon, right? So the only thing that's under this if is the first go to fail. So what that means is that we always execute this line of code. Or sorry, I shouldn't say always. If we pass condition 1 and don't go to fail here, and we pass condition 2, then we will go to fail, okay? So we'll go all the way down to here. Is there any way to reach condition 3 or condition 4? No, we always skip over it, okay? Now, let's say there's a problem with condition 3. what happens? We never check it. Okay. Now, another thing I didn't mention is, okay, when we go to fail, we return check. What's the value that's sitting in check if we pass conditions 1 and 2? 0, right? It's good. Okay. So just because it's labeled fail doesn't mean that you're necessarily failing. You're returning what's in check. Okay. So if I pass condition 1 and pass condition 2, check has a 0. I go to fail and I return it, and I never check conditions 3 or 4. So the code that calls it thinks all the checks passed, but in reality, just the checks before the second go to fail passed, and I don't know anything about the rest of them. Okay, so this is unreachable. Now, let's say that this is important code. Like, say it's checking all the things in a certificate, right? What does that mean? Well, it means it does some of the checks, and then if it passed those checks, it won't check anything else. Okay, so if there's a really important check that's in this unreachable code, it never gets checked. All right, and so what happened in this case is there actually was something very, very important in this code, which is, does the domain of the certificate even match the domain that you're visiting? That check was inside this unreachable code. Okay, so what does that mean? That means if I'm an adversary and somebody's running this Apple software, they try to go to google.com. I don't have a certificate for google.com. I'm not Google. Okay, but I do have a certificate for pulpspy.com. That's my personal website. Okay, so what I do is I just drop in my certificate instead. So the user gets it, right? They have a certificate for completely the wrong domain, but it is a valid certificate because I do own it. It is signed by a CA. That's fine. It's checking whether it's signed by a CA up here, right? But then it hits the second go to fail and it misses that basic check of, does the domain that is being visited even match the domain in the certificate? Yeah. And so you could literally take any certificate and just drop it in, right, with your public key, and it would accept it. Okay. It's kind of crazy. And this, we don't know how long this vulnerability was there. Actually, probably people have figured it out, but anyways. Okay, how do we fix this, just by the way? This isn't really about SSL, it's more about coding. So what we could do is obviously write better code, not have go-tos ever, or like not do those kinds of mistakes. Another thing that right after this was published, and it made the news, like it was a pretty big vulnerability, a bunch of companies that make static analysis tools said, oh, we took this code, now that we know the vulnerability is there, we took the code, we ran it through our tool, and our tool flagged it. It flagged that code was unreachable. And so shame on Apple, they should have used static analysis. They could have found this bug easily. But what they don't tell you, what the vendors don't tell you is it did indeed find that bug, but it found like 1,000 other things that weren't bugs, right? And so like these tools, like they mix all sorts of stuff together. And so even if you're using the tools, you sort of have to go through by hand and figure out like, is this actually real? Is there actually a problem here or not? So false positives are one of the things that makes static analysis not that great. The other thing that they didn't do, and this is what they really should have done, is they should have had unit tests where they just had a bunch of bad certificates. You know, and one basic bad certificate you might have is like a certificate for the wrong domain. And then every time you update the software, you should just run your unit tests and just make sure that it's not accepting certificates that it shouldn't accept. Yeah. And so, anyways, there's a bunch of people then that they unit tested all of these libraries, not just Apple's, but like OpenSSL and all of these. And then they started doing fuzzing and taking like pieces of certificate A and certificate B and like kind of mashing them together. And they found all sorts of like weird conditions where things would just crash for no reason. Or there were other problems, like it might accept a certificate that was like malformed or something like that. And so they fuzzed them and then they fixed all the vulnerabilities. And so now our library should be like a lot harder than they were back then. Okay, here's another vulnerability. Let's say that I have a certificate for pulpspy.com and it's real. It traces back to a root CA, but I'm not a CA. I'm not a CA certificate, okay? Now, what I could do is I could still sign a certificate, say, for google.com. And so when I see a user going to google.com, I drop in my google.com certificate that I signed, right? And I drop in my certificate and the certificate of my CA and the whole chain. So I drop in this chain, right? And the only thing that's wrong with this chain is just that the person will look at the Google certificate, it will look fine. Then they'll say, okay, who signed the Google certificate? They'll see my certificate. And it's fine, except for I won't have CA equals true in my certificate. Okay? So that's the only thing that's going to catch this error. Otherwise, it would go through. Okay? So one thing you have to do is you have to check that all CA certificates are actually CAs, right? It sounds like a pretty basic thing. In fact, it's called basic constraints in SSL language, like in the X509 standard that defines how standards or how certificates are standardized. They literally call it basic constraints. Anyway, so it should be set, CA equals false should be set in all site certificates itself, okay? But it's up to the software to check whether that's the case or not, okay? And so what happened is early in the earlier days of the internet, 2002, someone realized that, oh, Microsoft Internet Explorer, their library that underlies it, is not doing this check. And so anybody could, if you have a site certificate, you could just pretend you're a CA and you can go issue certificates and Internet Explorer is going to accept those certificates. Okay? So they just never checked it. All right? So this was a big vulnerability and everyone thought, okay, that's really dumb. Microsoft, you're dumb. Like that will never happen again. That's like a once in a lifetime thing where someone did something really stupid, but now we realize it, we wake up and that will never happen again. Then Apple said, hey, we have a new iPhone in 2011. And by the way, we wrote an operating system for this phone that's completely from scratch. Okay, it's not Mac OS or OS X as it was called. It's a completely new operating system. Therefore, we have a new browser, we have a new SSL library, like everything's new. And guess what? They forgot the exact same thing. Okay, so they didn't check that basic constraint. And then people said, okay, that's dumb, Apple, you're bad, it won't happen again. Then all these IoT devices started coming out. And again, they have a brand new operating system. It's some stripped down operating system. Somebody, they hired someone for 3 months to implement SSL and they implemented it and they put it on these and it's, it's hard coded into 10,000 devices that are out there. And guess what? They weren't checking basic constraints again. And so you could just, you could use any certificate in the certificate chain, even a site certificate. Anyways, it's not going to happen again. Okay, we learned our lesson the first 3 times. Okay, here's another thing you could do. What happens if you actually get a certificate that is for the wrong domain? Okay, or let's say you get a certificate that is not signed by a proper CA. So your browser checks it and it says, oh, I don't know what that CA is. Okay, it was signed by some CA, like Syria Telecom. That's not in my root store. I don't know what that is. Okay, is it going to let you go to the website? Is it not going to let you go? Is it going to show you a warning? Like how would it actually handle that case? What do you think? Warning. Okay, so that's what it will do. It'll basically say, okay, I got this certificate. I don't know what to do with it. I don't recognize it. It's not from a CA or the chain. It doesn't chain back to a CA in your root store. What do you want to do? Do you want to go to Facebook anyways? Or do you want to, don't ever connect to this website. It looks sketchy kind of thing. Okay. So a lot of times it's going to depend on what does the warning look like. Okay. So here's the actual warning at circa 2011 when this was noticed. So it says there's a problem with this website's security certificate. The security certificate presented by the website was not issued by a trusted certificate authority. Security certificate problems may indicate an attempt to fool you or intercept any data that you send to the server. We recommend that you close this website and do not continue to this website. Click here to close or continue to this website, not recommended. Okay. Now, first off, you probably understand what that error message means. Yeah? Because you just sat through 3 lectures about SSL. Okay. Before you took this course, maybe you didn't know so much what it means. And if you're not a grad student sitting here in a security, course-based master's, you probably have no idea what this means, okay? So you're just a normal, everyday user. Think of the cognitive walkthrough, put yourself in the shoes. You're not a computer expert, you don't know anything. Can you make sense of what this is saying? Probably not, right? I just want to go to Facebook. I woke up, I wanted to go to Facebook. and this is what I see. And to go to Facebook, all I just have to click this button, right? What do you think people are going to do? Not 100% of people, right? But a good majority of people will probably just click the button, right? And so what you could do is you could actually just openly attack SSL and just hope that people click through the warnings. Because if they click through the warnings, then you don't actually need a fake certificate. You don't have to hack a CA. You don't have to break the cryptography. You don't have to do anything, right? Just do the thing that like is bad and hope that the users, the usability is not good. So someone ran a user study, and basically the domain mismatch is this one here. And so they found that about 40% of people would just click through it, or up to 50 would maybe click through it, and maybe about 50% would not accept it. And this is in a laboratory setting where like you're being brought in and being asked these questions about it. Now, since then, what's happened is that browsers have responded, okay? So usually Chrome leads the way. So this was research that was done by people at Google. And they tried to do two things, basically. One thing is to make the message actually more intelligible to a non-expert user, okay? So this is a much better message. It just says your connection's not private. Attackers might be trying to steal your information. For example, passwords, messages, or credit cards. Okay, nothing about certificates, nothing about certificate authorities, SSL, no jargon, right? It's just like this is the attack that may be happening. And the second thing is it's not obvious how you click through this. Okay, so there's a back to safety. If I click that, it's like I don't visit the website, and I can click on advanced, but that's not like. That doesn't take me to the website, okay? If I click on advanced, then it shows me a little more information, okay? And now it starts talking a bit about certificates, and it gives me a bit of the jargon. So like for expert users, they could read this. And then way down here, if I click twice, then I can actually go to the website, okay? So the browser will always let you go because there's other reasons why like there might be weird things. Like say I'm just building a website and I'm just testing it. I don't have all my certificates set up or things like that. So the browsers ultimately will let you go if you really want to go, but it's a lot harder to click through this one than it was to this one, and it's a lot easier to understand as well. And then I think they ran some user studies and saw that the click-through rates went like down to, I don't remember what the numbers are, something like 5% or less or something like that. You can try it out. So this bad SSL website has all sorts of different types of things that could be wrong. So we looked at this website before. We looked at it in terms of mixed content. And then if I want to see the wrong domain, I have to find it. There's so many different things. So I think this is the one. So here, I just got sent a certificate. I'm trying to visit this website, and the certificate's for a different website. Okay, so this is what Safari, as of today, says. It says this connection's not private. The website may be impersonating this to steal your personal or financial information. You should close this page. You can see that the language is almost the same as what Google said. They probably copied it, changed it enough so that Google wouldn't sue them. But very, very similar. I can close the page. If I want to click through, I can't obviously click through from here, but I can say show details. And then down here, I can view the certificate. So you'll see that certificate name does not match input. So there's an error in the certificate itself. And then if I really want to, I can visit the website. Then it shows me yet another warning, like, are you sure you really want to visit this website? And then I can click through. Okay. Okay, let's see, how are we on time? I'll do one more and then we'll go for break. Okay, this is another just sort of weird issue that people found. It's based on parsing. Okay, so we were talking about how the domain in the certificate needs to match the domain of the website that you're visiting. What if the domain in the certificate is kind of weird? okay? Let's say it has special characters or things like that. Then what you have to do is you have to like parse it and decide what you're going to do with it. So here's an example of a weird domain that you might see in a certificate. Someone might go to a CA and say, will you sign my certificate? And the subject name is google.com null character.concordia.ca. Okay? So you're the CA and you're looking at that. And first you just got to figure out like, what is this domain? Like what exactly, what are they trying to register here, right? So how would you parse that as a string? So if you're looking at that string, what does that string mean to you? First off, can a URL actually have a null character in it? That's maybe a good place to start. So the answer is no. So some special characters are allowed now, but a null character is definitely not allowed, okay? So you can't literally have that as a URL. That's not a valid URL, okay? So you're the CA and you're looking at this, you see something that's invalid, what do you decide to do? Okay, so you could reject it, throw it out, say, try again, that's not valid, okay? What if you were very friendly CA and you wanted to help the person out, right? And you say, okay, that's not valid, but I think I know what you mean. Right? What do you think they might have meant by this? So you could just drop the character that's illegal. Okay? So I'll just drop it. Okay? So what does the domain become if I just drop that character? Yeah, but sorry, just tell me what domain is it? So it's google.com.concordia.ca. Okay, is that a valid domain? Why not?
Because Google have not related to the Concordia.
So that's true, but it's actually the opposite because which is the actual domain? So .ca is the top level domain, and then is it Google's domain or is it Concordia's domain? If it's google.com.concordia.ca. Okay, it's Concordia's, okay, because Concordia is at the end, okay? So google.com.concordia.ca is a domain of Concordia. It belongs to Concordia, correct? Okay, what about the google.com before the Concordia? Is that really not allowed? Yeah, it's a subdomain, right? Can I do mail.concordia.ca? Can I do images.concordia.ca? Can I do images.mail.concordia.ca? So I can have as many subdomains as I want, yeah? Can I do com.concordia.ca? Why not, right? I probably wouldn't, but why not, right? There's nothing wrong with that. And then could I have google.com.concordia.ca? I can, okay? So that's a perfectly valid domain. It's weird. And you'll notice, actually, if you go to a lot of phishing websites, they'll do this trick, right? So they'll be like, oh, facebook.com dot, some weird domain name, which is the actual domain. But they're just hoping that people read facebook.com and then see a bunch of garbly goop and don't realize that this is actually just a subdomain of another website, okay? So that is a perfectly valid domain. So if I drop that special character, that null, then I do end up with the domain. It belongs to Concordia. It's a subdomain of Concordia, okay? Is there anything else I might do with that string? So I could just reject it, don't like it. I could drop the character that I don't like and accept the rest of the string. Is there anything else that you might do with that? What does that mean? So parsing is just reading the string and knowing when to stop, basically. Yeah? Okay, what if I'm written in the language C? And I see a string like that.
Then you could read it into google.com and drop there.
Why? So correct, but why?
Because it's C.
Yeah, and C.
C doesn't, how it operates for string and parsing is when it sees the null character, that's the end of the string, so that's it.
Okay, so C is a language that's very bare metal, it's meant to be very fast, not a lot of overhead. And so when you put a string into C code, it's not like Java where you're like, here's a string, here's the start, here's the finish. You just say, here's where it starts in memory. Read it until you hit a null character. Then you'll know you hit the end of the string. Okay, that's how you'll know that you found the end. I can't even tell you where it ends. I know where it starts. That's all I know. So just keep reading until you hit a null character, and then you're done. Okay, so that's how you parse out a string in C. Okay, so a third way is these are called null terminated strings. Okay, so you could interpret this as a null terminated string. Okay, so I could reject the string. I could just drop the null character, in which case I end up with google.com.concordia.ca, which we establish is concordia.ca. It's a subdomain of concordia.ca. Or I could terminate at the null character, in which case I would go to google.com and then I'd be like, I hit the end. I would completely ignore the .concordia.ca, and I would think that this is google.com that's being requested. Okay? Now, which is the right way and which is the wrong way? Trick question. Okay, there is no right or wrong. Okay? The important thing is that everyone does the same. Okay? If everyone writes in C and does null terminated strings, there's no problem. If everyone drops special characters, there's no problem. If everyone rejects strings as soon as they see like a bad character, there's no problem. Okay? The problem arises when different people do different things. Okay? Your CA that you're asking the certificate from, they're written in C, they're doing one thing. Your browser is not written in C, they're doing a different thing, right? Or vice versa. My browser's written in C, I'm looking at the certificate thinking it's a google.com certificate, right? But the CA, when they signed it, they were just dropping the special character. And so when the CA signed it, they thought it was a concordia.ca certificate, okay? And because the person who requested the certificate did actually control concordia.ca, they were able to get that certificate with it, okay? So this is where the attack goes wrong, is if, forget about Concordia, pretend this is like evil.com or something like that at the end. So the attacker goes, they ask for google.com null character dot and then a domain that they control. The CA drops the special character. They say, do you actually control this domain? You prove that you do. And they say, fine, I'm going to sign your certificate. Now, when they sign it with the null character. Okay, so you present the certificate that you want signed. They do all their checks. And then when they're happy at the end, they just sign whatever you gave them. So they don't even know that there's a null character there. Okay, then you now have this certificate. And so you're on the web. You see someone going to google.com. You just drop in your certificate. It goes back to that person's browser. And their browser, say it's written in C, so it's going to terminate at the null string. It would say, yeah, this is a valid certificate for google.com. It's signed by a CA. I know the CA. It's in the root program and things like that. Okay. So you were able to get a certificate for google.com even though you don't control google.com. All right. So it's effectively a Google certificate. So this was pointed out as an issue. The consensus now is that we do one. Everyone does one. Browser does one. The CAs do one. If you see any special characters, you just don't. You don't try and parse it. You just give up. So that's where we are now. Okay, this is a good place to pause. So why don't we take 10 minutes, and then we'll come back and talk about revocation, which is the final little piece of this. Hopefully this won't take the rest of the lecture, but there's three other topics that we'll talk about. Okay, so the next thing we'll talk about is revocation. So what happens if there's an adversary in the middle, or sorry, just forget about in the middle for a second. Let's say an adversary steals your key. Your key has to be somewhere. You're actually using it every time you make one of these tunnels. So it has to be sitting on your web server. It's in RAM. Maybe I use Heartbleed, maybe I use something else, but somehow I'm able to get your key, okay? Now, what I can do is I can now intercept your traffic, okay? Let's say, though, that you notice. So you go in your server logs or whatever, and you realize that you're breached or you strongly suspect it, okay? What do? How do you recover from the fact that someone stole it? So the first thing you could do is you could just get a new certificate. You create a brand new key, you go to the CA, you get a new certificate, right? The problem is it doesn't actually fix the problem because the old certificate is still valid. So what will happen is you'll try to connect to Concordia. Concordia will send its new certificate, but then the adversary will just swap out the new one with the old one, the one that it knows the key for, okay? And as long as the old certificate is still valid, then Alice will accept it. She doesn't even see the new certificate, okay? So it's not as simple as just like you just update your certificate. You need to actually revoke your old certificate. You need to make it invalid somehow. Okay, so we need to cancel or revoke the old certificate. All right, so how do we get a certificate revoked? So the first question is who do we ask to revoke it? So what we'll do is we'll go to the CA that gave us the certificate and we'll say, okay, we want you to revoke it, okay? And what the CA will say is, okay, there's two ways that we do this, and both of them are supported to some extent. One of them is we just publish a list every now and then of all the certificates that we revoked, okay? And what the clients are supposed to do is they're supposed to go get that list every now and then. They'll go through the list and they'll see whether that certificate's on it or not, okay? The other thing is because these lists can get big, what the CA will say is, I'm going to put up a server, and if you want to know whether a certificate's revoked, just ask me, okay? So every time you get a certificate, you ping the server, and you say, here's the certificate I just got. Is it revoked or not? And the server will say yes or no, okay? So that's called a status check. Where do we know where that server is? Well, it's in the certificate itself. So if you go digging in the certificate, you'll see that there's a URL like oscp.globalsign.com/blah, blah, blah, blah. And that's the server that I go to ask whether certificates are revoked or not, okay? Okay, so this is fine. So this is one way of doing it. Now, imagine that you guys decide you want to be a CA. Okay, now you know it's pretty easy. There's this domain validated thing. You just have to put up a computer. It sends some emails, and if it gets the right responses back, it issues the certificates. There's nothing really special to being a CA. By the way, you get to charge hundreds or thousands of dollars for every CA, every certificate that you issue. And so this is a good business for you to be in. And instead of charging $1,000, you're like, I'm going to charge $10. Okay. And now everyone wants to be you. They want you as your CA because you're undercutting the market. By the way, you can get a certificate for free now. But anyways, just for the sake of the story, let's say Google signs up and Facebook and Twitter and all the X, I guess now, all the major websites, you're the CA for all of those websites. Okay. So you're doing really, really good. You're really, really happy as a CA business. Okay. Now, what happens every time a user goes to Google? What happens is they say, hi, Google, I want your certificate. Google sends it. And then the user says, okay, now I got to figure out whether the certificate's revoked or not. Okay, so where do they go? They go to you. You're the CA. Okay? And they say, is this certificate revoked or not? It's not revoked. You say no. Okay? Someone goes to Facebook. Then they come to you right after and they say, Facebook just sent me the certificate. Is it revoked or not? Okay. Now, how much traffic do you think Google does in a second or in a minute? Yeah, millions, probably tens of millions. I don't know what the numbers are. It's enormous. Okay. And Facebook and X or whatever social media, Instagram, whatever, TikTok, all this traffic, basically every user that goes to that website, they then turn around and ask the CA whether the certificate they just received is revoked or not. So the CA is getting the equivalent amount of traffic. Okay? Every user that goes to one of these websites then has to go to the CA. All right? And so what happens is the CA server just gets hammered. Okay? And our CAs in the kind of the infrastructure and the business of running, handling vast amounts of traffic? Probably not. Most of them aren't set up in that particular way. Thank you. So what ended up happening is that CAs had these servers. They were in place. They had the protocol. But they were just overwhelmed all the time. And so when you went and asked about a certificate, you would probably hear no response. Okay? It would just get lost in it. And so then browsers were in this predicament because users couldn't connect to these servers. And then browsers are like, okay, what do we do? The person's trying to check the certificate. They can't get a response of whether it's revoked or not. Are we going to throw an error? Because if we do that, we're going to throw an error on every single website, you know? And so basically what happened is browsers said, okay, we got to turn this off because if we are very strict about always getting a response, then we're just basically the user's going to get error messages all the time, or it's just going to hang. Users are going to get frustrated. They're going to switch browsers. They don't want to use our browser anymore. Okay. So the status quo became, we still try to do the revocation check. So we send the check, but if we don't get a response, we time out and then we just proceed as if there's no error. All right. That's the best that we can do. Okay. So we call this fail open. So there's a failure because we're not able to get the response. And when we fail in a way that's permissive or permit override or open. Okay. We could fail close. Fail close would mean if we don't get a response, then we assume the worst. Then we say, I don't know whether it's revoked or not, so I'm going to assume that it is revoked. Right? Fail open is, I don't know if it's revoked or not, so I'm going to assume everything's okay. All right. So let's say you're an adversary. You've actually compromised the certificate. The person caught you compromising it. They asked the CA to revoke it. The CA did revoke it. Okay? And so you're on the wire. You see someone, they're going to google.com. And you're like, I have a stolen certificate for google.com. You drop it in. Okay? Then you start sweating because the user's like now trying to go to the CA asking whether this thing's revoked or not. Okay? What do? You're in the middle anyway, so you see that message going by, you just drop it. Okay? You don't let them ask the CA whether it's revoked or not. Or if it slips through and the response comes back that, yeah, it is revoked, you just drop that. Okay? And then the browser waits a few seconds, it's not hearing anything, and then it just proceeds as if it's not revoked. All right? So it's very, very easy to do it. Now, the other thing you might notice that seems kind of weird is this is happening over HTTP. It's not going over HTTPS. All right. If it were going over HTTPS, first off, if it's going over HTTP, then you can also change the response. So if the CA says, yes, it's revoked, you can just swap it and say, no, it's not revoked. Okay. So why would they run this protocol over HTTP? Do CAs know how to support HTTPS? CAs. A CA does, right? A CA is issuing certificates for SSL. They're in the business of SSL. So they know how to run something over HTTPS. Why don't they?
It's the same issue we had earlier with the certificate because it's the establishment that you have to do to actually use HTTPS. So if you did it through HTTPS, you would have to go ask for the higher certificate with another link and so on and so forth.
Okay. So it's sort of like the thing we saw before where there's this kind of circular dependency. So basically what would happen is, I thought I had a picture of it, I don't. So what I'll do is, let's assume that this actually is over HTTPS, okay? So I go to I go to Concordia, and I say, give me your certificate. And Concordia says, here's my certificate. I say, okay, that's great. I just need to check whether it's revoked or not before I trust it. So I look in the certificate, and I see the OCSP responder, and I go there. And this is now over HTTPS, okay? So what happens is before I get the response back, what I get is the certificate to set up the tunnel so I can get the response, okay? So now I have a certificate, right? And I say, thank you, Global Sign. You sent me your certificate. That's great. But just wait 1 second. I have to see whether the certificate's revoked or not, right? Then how do I figure out whether it's revoked or not? Well, I go and I look in that certificate and I get some other URL for whatever OCSP responder is in their certificate. Then I go to that OCSP responder and I say, I want you to tell me whether the certificate's revoked or not. I want it over a secure tunnel. So to set up that secure tunnel, send me your certificate. They send the certificate, and then I have to say, well, is this certificate revoked or not, right? And then to learn whether it's revoked or not, I have to go to another HTTPS website, and so it never ends, okay? There's no way out of that loop, okay? So it ends up being a sort of infinite loop. Okay, so let's see. Yeah, okay, and because it goes over HTTP, then you can just change the response. So I can ask about a certificate, is it valid? The CA says no, and I just switch it to a yes, and that's fine. Okay, so that's OCSP. So it doesn't really work that well. It fails open. If you don't get a response, it's over HTTP. It's not a great protocol, okay? The second option we can do is the CA can just publish a list of all revoked certificates, okay? There's a bit of a performance hit where I have to go and download all these lists. I have to know about all the CAs in order to get the lists. Or maybe the first time I see a new CA, then I'll go ask for the list. That's fine. The lists are also in the certificate. So every certificate will say, here's the URL where you can get the list, and here's the URL where you can ask your OCSP status requests. And then what Google said is they said, you know what, we're going to go and we're going to collect these CRLs for the user. Okay? Instead of the user doing it, that's kind of crazy. We'll just gather it for them, and then we'll put it into Chrome. And then every now and then, I don't know, every 3 days, I don't know what cycle they do it on. Let's say it's every 3 days, we'll push a new update to all the Chrome users. It will just be kind of like a software update. You don't have to click on it or anything. It will just sort of happen in the background. And then now you have the new CRL list, or it's called the CRLS set, okay? And so this protocol works pretty well. It protects users. Oh, and then they said, we'll just turn off OCSP because people don't honor it anyways. The only problem with it is that there's so many CAs in the world, and I don't know if the issue is that it can't be that they don't know about them. It's maybe that the CAs aren't actually publishing the lists or as timely, or I'm not exactly sure what the exact issue is, but the percentages of CAs that are out there that were not in these lists was something like 75% or 85%. So most CAs didn't end up in this list, whereas the ones that were in the list were actually like a minority of all the CAs. Now this data is kind of old, so I don't know, maybe it's better now. But anyway, so this whole thing was a good idea conceptually, but I'm not sure how good it is. Then what's happened more recently is the browsers have gotten more persistent with CAs about making sure that they're responsive here. And so what they actually did is they went back to these EV certificates and they said, okay, we're going to reset like how we do EV and DV certificates. And one of the new rules for EV certificates is you must have an OCSP responder and it must not like drop things. Then we'll let you have one of these certificates, otherwise we won't. Or we'll let you issue those kinds of certificates. Now there's a third option that's actually really, really nice, which is that, let's say Google's about to send you their certificate. What they could do is they could go on your behalf to the CA over OCSP and say, is this certificate revoked or not? And the CA will say, no, it's not revoked. And then they'll say, okay, can you sign that? And so they'll say, fine, we'll sign it. So they sign you an OCSP that says it's not revoked. There's a timestamp on it. And then when you come to Google, as you're connecting to Google, they send you both their certificate and they send you the OCSP. They staple them together. So basically you get a certificate and you get an attestation that it's from the CA, it's signed by the CA, that says this is a fresh certificate. Or it's fresh, we have a fresh statement that it hasn't been revoked. It hasn't been revoked as of this timestamp, and this timestamp's only a couple hours old, okay? And then what happens is Google can do that for all their 100 million users that are connecting to them every second. And so none of those users have to go to the CA anymore. Google goes once for them, and then the users all get it. Okay. This is a great idea. It should work. The only problem is that network devices aren't expecting it. It breaks the standard of how certificates are communicated. And so they tried it. Google experimented with this, but they found that like lots of people had like routers at home, like Wi-Fi routers, and they would just break if they saw one of these things stapled in. And then users would get frustrated because their Wi-Fi router is breaking. And so, yeah, that's the issue. Okay, so that's revocation. Questions about revocation? Okay, yeah.
What if I block all the Google services from my browser and my browser is not getting any uploads from Google?
Yeah.
What happens in that case?
Yeah, so you'll have a stale CRL. So you'll have a CRL list that's stale. And so if something was revoked since you last did it, you won't know about it, and then you'll accept it as not revoked. Yeah. So that's an attack as well. So the adversary could try to just, if they see these CRL lists coming down and they know that it contains one of the certificates that was revoked that they stole, they could try to drop that update. And if they're able to successively drop it every time, then the user will never update, and then they'll accept the revoked certificate. Yeah. But the difference between that and this, like dropping a response here, is here you're doing it in real time. Like the user's connecting to the website, you see it happening, and then you drop the response right away. So you just have to be on the wire for that like split second. Whereas if you want to drop all CRL set updates, you would have to stay on the wire, you know. And I don't know how often Google would try and send it, but they might try and send it once an hour or something. So you'd have to continually drop it. But yeah, but it's the same principle would work for sure. Okay, another thing you could do is just not use a certificate. Okay, what do I mean by this? So I want to take you back in time a little bit to how the web used to work. It's not the way it works anymore. But normally what would happen is you would go to concordia.ca, and Concordia would say, okay, we have this sign-in option, and in order to sign in, you're going to have to send your password, and we need a secure tunnel. We're not going to let you send your password in clear text. Okay, that's fine. But before you sign in, we don't need the secure tunnel. Okay, if you're just going to Concordia and you're browsing and you're not signing in, then that can just go over clear text. And then as soon as you want to sign in, we'll swap you over to SSL. We'll set up the secure tunnel. We'll take your password off of you. And then, I don't know, maybe we switch you back, or maybe we just keep you on SSL, because you do have a session cookie at that point. So they should keep you on SSL. But anyways, so tons and tons of websites work this way. You would just go to them. And a lot of them, they would literally have the username and the password field like right in the website itself. And that's a website that you downloaded over HTTP. Okay, so you would type your password and your username into an HTTP website. You would hit enter, and it would do the right thing. It would switch you over to HTTPS in order to send the password. But the question is, from a usability perspective, how do you know the website's going to send you over HTTPS? So when you hit send on that password, how do you know it's going over HTTPS as opposed to HTTP? And so the answer is there's no way to know unless if you inspect the source code of the website. If you look at the source code of the website, you can see that when that button's pressed, it goes to a URL that's over HTTPS, but there's no actual indication on the website itself. Okay, so you could see, oh, there's a sign-in button. There's a website that's attached to this sign-in button, and it happens to be HTTPS as opposed to HTTP. Okay, now what the adversary can do, what can the adversary do? So the adversary doesn't want your password to go over HTTPS. Okay, they would rather it go over HTTP because then they can read your password and they can steal it. All right, so what they can do is they can sit in the middle and sense whether or not this button goes over HTTPS or not is inside the HTML of this website. Okay. What they could do is they could actually change the HTML. So if they change the HTML and they wired that up to an HTTP button, then when you pressed it, your password would go over HTTP. All right. Now you might realize it as a user. You might be expecting to see the lock after you hit submit, but at that point it's too late. Okay, you've already sent your password. It's gone across the wire. You can't get it back. All right. So how hard would it be? I mean, this sounds kind of crazy. You want to go into the HTML and figure out where the button is, and you want to replace it with HTTP. Like that sounds like a pretty sophisticated attack, right? Okay. But it turns out it's actually very, very simple. All you do is you go through the HTML document, and every time you see HTTPS, you just change it to HTTP. You have no idea what you're doing, but you just change every link that you see to HTTP. Then you will also hit the link that will be attached to the sign-in button, okay? And then when the user clicks on it, it will go over HTTP instead. Okay, so this just says like replace all instances of HTTPS with HTTP instead. Okay, so we call this attack SSL stripping. So the idea is just the adversary sits in the middle. They run kind of like a deep packet inspection because they have to look at the HTML files, but it's still a pretty dumb machine. It doesn't really know what websites are. It doesn't know, it certainly doesn't know what a button is on a website. It doesn't understand what websites are. It just sees that HTML is a kind of text file. And if I search through that text, sometimes I see the character HTTPS. And every time I see that character, I'm just going to replace it with HTTP. I'll just drop the S. Okay? And what effectively you do is you strip all SSL off of it. So the user goes to a website not over SSL, and they'll never end up on an SSL website no matter what they click on, because all of the SSL links have been stripped out of the website. Okay, so once you're there, they can basically keep you there, and it's like they move the whole entire site off of HTTPS to HTTP. Okay, here's another attack. This is called picture-in-picture, which sort of gives you an indication of what it is. Okay, so I'm on this website. Well, actually, I have two windows open here. So I'm on some website. Say this is like a bad website on the outside, an adversary's website. But then I have a website here to paypal.com. You can see it's green. It's an EV certificate. You may not be able to see it, but there's a lock. Everything looks good. Okay. There's an email address and a password field. If I put my email and my password and I hit login, is that going to go over SSL, yes or no? So I'm on this website. There's a password field. I'm going to hit login. Okay. And I'm already on SSL. Okay. And it's paypal.com. It's an EV certificate, so I even know that this is PayPal US, the company. It's not some weird PayPal. Yeah.
Depends what the outside website is running on. If it's on HTTPS, it will be. If it's not, it will be.
Okay, why does the outside website have anything to do with this website? This is just another browser window.
Because it's not in reality. Because we're mentioned that it's a picture-in-picture attack. So what this means is that it's a web page designed to look like another web page is inside it.
Okay, so is this actually a browser window, this inner thing that you see? Is this a second browser window that's open? Is it possible that it's not? Okay, it's completely contained in this outer website. Could this just be an image on this outer website? You're looking at a website and there's just a picture there. It looks like a browser window, but it's not actually. Yeah? So it could be, and it could be not just an image, it could be it could have text fields and buttons, and even if you click on things, it would pop up and things like that, okay? So are we sure this is even a browser window? Maybe is this part of the outer website? Okay? So we don't know. Now let's say it is part of the outer website, right? The fact that there's a lock here and all this stuff, that's just images on a website, right? It doesn't mean anything, okay? So if I put my password in and click login, it's going straight to this URL, all right? How do I test it? Is there any way I could know? I get this feeling, maybe that's part of the website. So what would you do to test it? Okay, so I could drag it. Let's say it does wiggle. So I click on it and I start dragging it. It does move around a little bit. You could do that with JavaScript as well. So you could do it, yeah? So we could inspect the HTML, but even simpler.
It will always be inside.
Okay, so I need to drag it outside of, so if I drag it all the way over here outside of the website and it goes, then I know it's a separate window. But if I drag it over here and it stops here or just it won't leave this area here, right, the gray area, then it looks like it's probably like something in the website itself. Okay, so we call this a picture-in-picture attack. So basically, you spoof what looks like a website, not just a website, you spoof what looks like a complete browser window, but it's actually in the content of the website itself. It's not a separate browser window, it's just part of the website. And any information that's put into this, you don't know where it's going. It's going wherever it's programmed to go by the outer website, which could be malicious. Okay, so we see this a lot. Now it's more like you'll see like little error messages and stuff like that pop up. And there's two ways this happens. One is you can ask the operating system to display something, but in this case, you can't really control what the buttons. You can control this text, but you can't control what the buttons say. And so they'll try and put the fraud in the text itself. But the other thing you could do is you could just spoof that like user interface on the website itself. So sometimes you might go to a malicious website, say you use Windows, and you see like a bunch of Mac window things pop up, or vice versa. Then you know it's a scam as opposed to a real indicator. All right. As a result of these types of attacks, now pop-up windows are basically not allowed. Okay, so browsers have tabs. They'll open things in new tabs. The reason they put it in new tabs is to prevent attacks like this. Also, tabs are just a little nicer and more usable in general. Okay, so it's you basically can't get a true pop-up window anymore, but they used to be more common. Okay, so if we throw this into our tree, we had all the ways earlier from class that we could get a valid certificate. We could just use an invalid one, either because we know it's going to throw an error, but whatever, users will click through the error. There could be something in the implementation. There's some cryptographic attacks we didn't talk about. We could try to steal a certificate, it gets revoked, and then we do something about the revocation. So we stop the user from seeing the revocation. Or if we don't have a certificate at all, what we could do is we could implement SSL stripping. So we just strip the websites of all references to HTTPS, hoping that you start on HTTP. We could do one of these picture-in-picture attacks. There's other things you can do too, like you can put locks all over. You could have like a website that isn't over HTTPS, but you have locks in the content of the website, so that you think the user thinks that because there's a lock, there's a lock here on this button that it's going over SSL, even though that doesn't mean anything. So yeah. Okay, so the full attack tree from the last three classes, you can go, it's on Moodle or it's here as well. It's kind of big to see. But anyways, you can see that we talked about a lot of stuff, okay? So there were a lot of different attacks that you can do on it. And what's the point of this whole exercise? So going back to attack trees, we started talking about attack trees because they are a methodology for you to find attacks, okay? They're a methodology that's very general. You can use it for software, you can use it for hardware, you can use it for anything, okay? And it can be as detailed as you want it to be. So we did the one with the parking garage, like you drive through the arm or whatever. Like that wasn't very detailed. I don't know how parking garages work in a lot of detail, but you can do attack tree sort of for fun and do it at a high level in terms of brainstorming. Or if you really know a protocol inside and out, you can go into a lot of detail as well. Okay, so it's not a methodology that's really limited by the methodology itself doesn't limit how technical you want to make it. You can make an attack tree as technical as you want it to be. And it's also nice because in this attack tree, there's all sorts of different attacks. So some of them are social engineering where you trick someone. Some of them are like get a government to go to a CA and take it over legally. And then some of them are like go into, how C++ parses strings as opposed to how Java parses strings and do some null character stuff. Like there's some are like deeply technical, some of them are like super high level and don't involve technical things at all. And all of them fit into the same tree. Okay, so you want a methodology that's very flexible, that you can, it's not just for technical things. It's for technical or non-technical, basically anything that you want, okay? And then attack trees are nice because they might help you see new attacks. So in particular, when you have structure, like here, we kind of fell into a structure where we're like, okay, we want the tunnel pointed at us. We could use an invalid certificate. We could use we could use a valid certificate. We could get an invalid certificate. We could get a revoked certificate. We could use no certificate. So you start seeing a pattern. Then you're like, well, is there any other kind of certificates? What about an expired certificate? Like I don't have a branch of the tree for that. But that's obvious because now I see the pattern. Okay, so putting stuff into patterns helps you see things that you might be missing. So that's the other advantage of the tree. And then the final thing is that it tells you a story when you go from a node to a leaf. So just to sample this, let's say my goal is to read information that's going over HTTPS. All right. I'm going to do that by getting the tunnel pointed at me. How am I going to get the tunnel pointed at me? Well, I'm going to get an actual certificate, okay, for it. How am I going to do that? Well, I'm going to go to a CA, and I know that they issue certificates to websites, and somehow I'm going to trick them into thinking I'm Google, even though I'm not Google, okay? I'm going to ask for one of these certificates that's automatically validated, and when they ask me how I want to do it, I'll say, send me an email at admin, send me an email at sslcertificates@live.com. And oh, by the way, I was able to register that. And so now I have the certificate. Okay. So that's the story. And then you can go backwards. Once I have this node, I've reserved this email, then I pass the email-based validation. Because I pass the email validation, the CA is going to give me a DV certificate. The DV certificate is going to be a valid certificate. There's nothing wrong with the certificate. And once I have a valid certificate, I can end the tunnel at me. And if I can end the tunnel at me, then I can observe the traffic that's going over. Okay? So you can read the tree in either direction, and it sort of helps you out. Okay, so that's everything. So it was a sort of deep dive into it. But anyways, is there any questions about any of this stuff? Otherwise, we're going to move on next class to a completely different topic.
When you were mentioning about the backtracking,
Yeah.
there are like tasks to be done on each side. It's not direct backtracking.
So it's direct in the sense, like I kind of skimmed over a few things, but it is direct in the sense that you do go to every predecessor
But then
node.
each step you have to do something more to get to the.
Yeah. So the backtracking it's not about knowing where the attack is. Okay. The backtracking isn't about the attack. It's not about how you defend against the attack. All it is about the story about the attack. So my goal, like say I write this report for you, I want you to understand the attack. By putting in an attack tree, you can read it forward and you can read it backwards, and it helps you understand the story of the attack. So that's all it does. It's just about like communicating what the attack is so that you get a better sense of what the attack is. But there's no magic to going backwards or forwards in the tree. Does that make sense? Yeah. And that's where you would use an attack tree is like you want to communicate to someone else what all the vulnerabilities are with whatever they're doing. You might do it in an academic paper. You might do it in a course project, something like that. You want to show these are all the attacks that, at least that I can think of. There's also no guarantee that this is complete, right? There's new attacks that are going to come out in the next 5 years that aren't in this tree because I never thought of them. Someone else is going to think of them. But anyways, yeah. Okay, other questions or comments? All right, good. All right, so I'll see you all next week. Next week we'll talk about social engineering, I think, next.